Hello everyone, it is February 25th, 2022, and it is Geo-Rant time. Geo-Rant number 155, structural basins. There's a couple of things prompting this episode, and I'll probably edit it because my drawings aren't always as good as the actual figures are. We've been talking a lot about language and usage of language and terms utilized, and without going down any deep rabbit holes and staying somewhat on topic, I just need to say that we all are aware and need to be aware that professionals, and I've talked about this recently, often use terms in ways you don't in everyday speak. Now, we try to, when we educate the public, use generic terms, or if there's a specialized term, we'll try to define it, but that doesn't always happen, especially if we're talking just to other geologists and earth science professionals. And I tossed around for a while how I can show this. And a couple of different terms came to mind, but then I remembered someone asking me about these a long time ago. So I'm going to show you what one is from a structural geology standpoint, and how it's not necessarily the same thing as you might be picturing in your head. Now, as you can see here, I wrote structural basins, but when we're in structural geology, we rarely actually use that word in front of it because we know we're talking about structural basins, so we just say basins for brevity purposes, and this is done a lot of times. Now, when you think of a basin, and you can comment below if you want or see if I'm way off base. But before I knew anything about geology, when I heard the word basin, I would think of a bowl or something like that. So I would assume it was basically just some sort of low area on Earth. I know the definition of lakes involves, a water-filled basin. So some sort of depression in the Earth. Scale doesn't really matter. And I think that's a definition most people have. However, in structural geology, that's not exactly what it means. Structural basins start out as what you would think of as a normal basin on Earth, just a low-lying area, but they don't end up that way and they don't have to stay that way. Two very well known, at least in the Midwest and globally actually, two basins, the Illinois, also known as the East Interior Basin, and the Michigan Basin, are two very large basins in North America. Now, those of you who have driven through Illinois or Michigan, the lower part of Michigan, might be like, doesn't look like there's a big deep depression here, even though these things take up nearly the entire state and often parts of neighboring states. So where's this basin Steve's talking about? That's because in geology, when we say basin, we are usually talking about structural basins. Now, structural geology, just for those of you that don't know, is a very complex subject, and it's the reason why most of us, even to get a bachelor's, have to have calculus. It's a lot more like engineering. We use the same principles, actually, as a lot of engineers do. We just apply them to the natural world. And as you can see, this is not just rock identification. This stuff gets complicated. So there's all kinds of subdivisions of geology that you may not even be aware of. And this is one most people actually aren't. Even ones who, like a lot of my viewers, are actually pretty astute in their concepts of geology. Now, a structural basin in geology, or just basin, starts out as what you think of a typical basin. And it's a low area compared to the surrounding topography in a lot of cases. So usually when we think of basins, at least Paleozoic ones, like these two massive ones here, they were deposited in a time when the oceans, the seas, were invading the land because the continents were a little lower in elevation, lower in sea level than they are now. Now, the reasons for this are complex and are not a talk for this time, but the basins would start out as a low area. So you would just basically get, you would have, this was a generic cross section. You would get, for whatever reason, a basin forming in the middle of the continent. This could be because of stresses externally. It could just be because of really high sea level, no ice caps, stuff like that. But you get a basin, generic cross section, whatever. And we'll say that the sea is coming in this way. So we're trying to do a three-dimensional thing here, because if I make it two-dimensional here, you're probably going to get confused, and I don't want to do that to you. So the seas are coming in this way. They're transgressing over this basin. So as the ocean sees, in geology, we'll often use the term sea to mean ocean or piece of the ocean. It's just generally something we tend to say instead of ocean. We're talking about marine deposits on land. But anyway, so you get the sea coming in. And what's going to happen in this basement? Well, erosion is going to take place somewhere. Now, this basin could be somewhat restricted, and you can have land on this side, even land on this side. Basins like the Michigan Basin are what we call bullseye basins, and those are actually pretty hard to explain. But those are textbook basins. The Illinois Basin isn't. It's more of a deformed spoon shape. So you don't have to have a nice, consistent bowl shape to have a basin. So anyway, you'll get this. And what will happen is, and remember, this topography I'm going to be drawing is greatly exaggerated. And I've actually done this before, I think in a previous Geo-Rant, taken a cross-section of the Illinois Basin or some other basin, maybe it was the Illinois Basin in Indiana. But anyway, we do this in vertical exaggeration so we can see what's going on. So it makes the dips look a lot steeper than they are. But if you do a 1-to-1 ratio, they'll essentially look level. And when you're in the field, your brunt and compass can't really measure anything less than a couple of degrees. There's kind of a sort of way you can do it, but it's not very accurate. So generally, anything with less than a 2-degree dip or so, we just say it's level. And if we're just mapping a restricted area, because the Illinois Basin, Michigan Basins are huge, statewide things. If we're just doing a little, quadrangle map, which is roughly the size of a township, so 6 by 6 miles, 10 by 10 kilometers, not all of them, but just roll with it. It doesn't matter. It's essentially where we are. It's flat and level. So we start to get sediments, detritus coming in, and we'll start getting, maybe a sandstone or something like that in here. And we may actually get marine carbonate deposits. So we start to get things like limestones being deposited and things like that. All right. And if these basins persist for a long time, obviously you can see eventually the basin is going to fill up with sediments. Doesn't really matter if they're sandstone, limestone, evaporites, shale, siltstones, whatever. It's going to slowly fill. But usually these basins persist for a long time. So you can't just sit there and say, well, the continent was so low that the basin just filled gradually over time. That's also not what we see, because what'll happen is you'll get unconformities within there and things like that. The basin will actually subside. Like the Illinois Basin goes far below sea level. So does the Michigan Basin. I mean, these things would have filled up really quickly if they were just a basin poofed into existence and sediment started pouring in. And we don't see those kind of deposits, and the fossils and everything like that show us it took millions of years to get this. Now, as you can see, I'm forming something here, okay? This thing, our basin is becoming filled with sediments. We're forming layers. I'm gonna have to change up a little bit here to show you the subsidence and more of what we get with that subsidence. So as that subsidence continues and sediments more and more fill the basin, well, this isn't going to continue indefinitely. Eventually, the basin's going to become starved. It's going to become cut off, sedimentation will stop, or the basin will just fill from sediments because subsidence stops. But this is just a generic cross-section of what a structural basin looks like undeformed. This was our basal part. Now the vertical exaggeration here is like 20 times, maybe 10 at the least, but 10 to 20 times. So you'd be on the surface here and you wouldn't even know you're on a structural basin, but you're on a basin. And now we can recognize these things in the field because, erosion has usually taken place significantly since then. So what will happen is you'll get topography, and we still have our green unit, so I'm going to use that here. Erosion takes place, whatnot, subsidence stops. There's your little bit of topography. I think you get the picture. So now you can see that we have some beds here reaching out to ground level where they were buried before. That's what uplift does and erosion does. So we recognize these things, and we'll look on a geologic map, and in this case a basin is essentially a closed syncline. For those of you that know what a syncline is, it's basically, we'll just do an asymmetrical one like this. I've done synclines before, so it's a cross section. They look like this, and they could be open, closed, whatever, but they'll have an axis here, down, running down and up from the tip of the nose. In basins like this, you don't really have a nose. You don't really have an axis. Now, some longer ones will try to, extrapolate one, and we can, but ones like the Michigan Basin that are very bullseye, you're never going to see anything that even can be drawn in as an axis. If we take our cross section of our basin, VE equals vertical exaggeration, 15 times, and I make two map or plan views, top to bottom. And I just put some random scale bars here, I guess north can be this way if you want. And they're vague analogs, Michigan Basin and Illinois Basin. This is not exactly what they look like. This is an oversimplification. Now you look at these and see about 10 kilometers here. Let's just say it is 10 kilometers. It's not meant to be exact anyway. What do you notice about this? Look at the layers involved here. What you can see our original landscape where our deposits were deposited. And in both scenarios, this should be a darker green. It started getting lighter for some reason, but this is this color, this is this color. What do you notice? The bottom forms the outer ring in this. And this is what our basins would look like if we were to traverse and walk across them or drive or whatever. It's a bird's eye view. You notice that the oldest part's on the outside. And you move in, and then you see red, red, and then you see purple, purple, and then you see light green in the center, like it is here. This is the center of our basin. From a cross-sectional standpoint, here it's here, and here we don't really have a fixed center. But so, it's about right here though, for argumentative purposes. What do you notice about that? Well, they're the same in both. The basinal structure is like this for every basin. Your oldest rocks are on your outside and your youngest rocks are in the middle. So how do we know that? Well, even if we didn't have radiometric dating or we didn't have the ability to date with fossils, we would still know that this is the oldest on all of these. How do we know that? Our basic laws of stratigraphy. Now, this concept covers a couple of basic principles or laws in geology. We cover the law of original horizontality here with this one, and the law of superposition. They're both used in this. Now, what those essentially mean is, in a sedimentary environment in this case, although you can have superficial lava flows, intrusions, igneous rocks, and things like that do not follow these. Well, it doesn't follow the law of original horizontality anyway. But basically, what that says is that in an undeformed sedimentary environment like our original basin, your oldest are going to be in the bottom and your youngest are going to be at the top. So when we develop these laws of stratigraphy, looking at stuff like this is how we kind of figured that out. But how would we know that? I mean, even, now we have radiometric dating, fossils, correlation, all that stuff. But how would you know that? Well, back to structural geology 101 is you look for up indicators. See, sedimentary rocks like to have things like ripple marks on them, mud cracks on them. And I've made tons of videos where I've actually taken you in the field and shown you how we find an upward direction when we are in the field. And when I mean upward, I mean originally upward, depositional upward. Now there's places where that upward changes very drastically, like here, this is the top here, and here, and here. Here it's pretty ground oriented. Here it's not. So when we talk about younging direction or stratigraphic up, structural up. This is what we mean. And we can tell by ripple marks, mud cracks, worm burrows, things like that, which way is up. Because in worm burrows, you get a sedimentary layers, generic cross-section, generic symbol for worms. Worms in a marine bed, they want to be able to access that water. So we know if we see them like this, that this is the top of our bed. You know, they're not going to be upside down. You can't deposit that upside down. Same thing with mud cracks. Mud cracks, cross-sectional view here real quick, like to form on the surface of beds. They don't form on the bottom of beds. It's a generic cross-sectional view of mud cracks. Obviously, on a plan view, you know, they're more hexagonal looking and they look more like a checkerboard. So this is the kind of things we use. We can use ripple marks as well. So we use those to determine up, younging direction. So even without the modern techniques we have, this was figured out a long time ago using simple observation. Now, it was never etched in stone, if you will, until we could actually date things. And these things cross-check one another. We never suspect a bed at the bottom of a basin, you know, say it has an ash bed in it, you know, we suspect it to be the oldest, this would be the youngest, and we have ash bed here, and we have an ash bed here, we date this. We never get this older than this. That has never happened. This is always older than this. That strengthens our principles, backs them up, shows them they're an accurate representation of reality. We can recognize structural basins on ground if we see a circular type structure or it's suggested through drilling, and the youngest beds are towards the middle and they get older as you go outward. Now, something which I may or may not talk about in the future is a dome or a closed anticline, and it's the opposite. You get the oldest beds in the middle and the youngest beds on the outside. But those are formed when there's actual tectonic deformation through compression. Domes can also form by something coming up from underneath. And I'm not going to address impacts here because impacts will also form structural basins. But the fact that depending on the size of the impact or the age, whatnot, what's still exposed, what's intact, what's been eroded, etc., they get a lot more complex than this. This is just a basic, simple explanation of what a basin is and how when we say basins in structural geology, you know, when a structural geologist talks about basins, this is what we're talking about. So, but when you go to like a geomorph guy or a geography guy, when you say basin, they're going to think of a lake basin or something like the basin in Rage province. They're not going to think of this. And even though we're all doing geo and earth science, even within that, we use things differently. Anyway, that was it. If you have any questions or comments, please leave them below, and I hope you learned something.